All right, let's dive straight into this explainer. Think of this as your high-yield, ultimate cheat code toolkit for absolutely acing the physics measurement questions on the ROB Technician Grade 1 exam. We're taking that dense, heavy textbook material and distilling it down into pure, actionable strategy. So whether you're totally overwhelmed or just looking to seriously sharpen your edge, this is where we build the foundation. We're going to learn how to spot those tricky exam traps and conquer test day with total confidence. We've got a lot to cover to build this masterclass toolkit today. We'll quickly hit base systems and SI units, decode the rules of significant figures, tackle math with those sig figs, introduce the principle of homogeneity, and wrap it all up with deducing formulas.
Okay, kicking things off with Section 1, Base Systems and SI Units.
So unit is simply our internationally accepted standard. Let's be real, without units, numbers mean absolute nothing. Now, history gave us a whole bunch of systems. You might recognize the CGS system using centimeters and grams, the FPS system relying on feet and pounds, or the MKS system with meters and kilograms. But the world, and more importantly your exam, now overwhelmingly relies on the SI system. It's a standard because it operates on a highly convenient decimal-based system, which makes conversions an absolute breeze. Now take a look at these 7 base SI units. What's truly fascinating is that final column on the right. In 2018, the global scientific community made a massive structural revision to this system. They completely stopped defining units by physical objects, so there's no longer a literal chunk of metal sitting in a vault in Paris defining a kilogram. Instead, they anchored everything firmly to unchanging physical constants. For example, the meter is now locked to the exact speed of light, and the kilogram is defined by Planck's constant. It's a beautifully precise system that literally never changes.
But wait, in addition to those base 7, we also have 2 supplementary units, plane angle, measured in radians, and solid angle, measured in starians. These are geometrically derived, and here's a fascinating quirk you absolutely need to remember for the exam. They possess units, but they have 0 dimensions. None, because they're defined as a ratio of lengths, like arc lengths divided by radius. The dimensions just cancel out completely.
Moving right along to Section 2, Rules of Significant Figures. Look, I know significant figures can be a massive headache for students, but they are incredibly critical. They basically act as a tracking system for the precision or the least count of whatever measuring instrument you're using. They tell us exactly how confident we are in a specific measurement. It's just all the digits we know for sure, plus one final digit that acts as our best estimate. So the trick here is just mastering these 6 counting rules. The first few are super intuitive, right? Non-zeros always count, and zeros trapped in between non-zeros count. Leading zeros, they never count. They're literally just showing you where the decimal lives. But watch out, because trailing zeros are a huge exam trap. If there is no explicit decimal point, like in the number 12,300, those trailing zeros do not count. But if you see a decimal, like 3.500, those zeros absolutely do count. And finally, keep in mind that exact numbers, like the number 2 in a math formula, have infinite significant figures. They will never limit your precision. Now, if you are doing unit conversions and getting totally lost in those trailing zeros, use this hack. To completely bypass the confusion, just switch to scientific notation. Write your number as a times 10 to the power of b. Here's the magic. Every single digit you write in that base number a is significant. You can completely ignore the 10 to the power of b part. It just makes tracking your precision completely effortless. Quick aside before we get to the math. What happens when you're rounding off and the number is exactly a 5? If the digit you're dropping is greater than 5, you round up. Less than 5, you leave it. But exactly 5? You gotta use the odd-even rule. Look at the digit right before the 5. If that preceding digit is even, just drop the 5. Leave it as is. But if that preceding digit is odd, raise it up by 1. It's a beautifully simple rule, but I promise you, it shows up constantly on exams. Which brings us perfectly to Section 3, Math with Significant Figures. Pay close attention here because it's a tale of 2 completely different rules depending on your operation. When you're multiplying or dividing, your final answer cares about the total significant figures. It has to match the original number that had the least number of total significant figures. But when you are doing addition and subtraction, you completely ignore total sig figs. Instead, you strictly look at the decimal places. Your final answer must match the number with the fewest decimal places. Don't let them trick you into mixing these 2 up. And listen, here is a massive pro tip for your exam.
If you want to avoid a huge trap in those complex multi-step calculations, always retain one extra digit during your intermediate steps. If you round off too early, your rounding errors are going to snowball, and you'll end up picking the wrong multiple choice option. Hold on to that extra digit and round off only at the very final answer.
All right, let's jump into Section 4, the principle of homogeneity. Before we can actually use this principle, we have to understand dimensions, which are denoted here by those square brackets. Dimensions are just the powers or exponents to which base quantities are raised. For instance, force is mass times acceleration, right? So we map out its dimensions as m to the 1, l to the 1, t to the minus 2. This simply shows us exactly how those base quantities combine to build the whole concept of force.
So, enter the principle of homogeneity. Think of this as your ultimate infallible physics lie detector. It dictates that you cannot add velocity to force, just like you can't add apples to lightning. Physical quantities can only be added or subtracted if they share the exact same dimensions. Furthermore, in a valid equation, every single term on the left-hand side must equal the dimensions of every single term on the right. Take that standard kinematic equation there, for example. Even though it looks a bit complex, when you break down the dimensions, every single term separated by a plus sign identically reduces to L, representing length. That right there is dimensional consistency. Now check out this golden rule. A dimensionally wrong equation must be wrong, but a dimensionally correct equation need not be right. Why is that? Well, because dimensional analysis completely ignores dimensionless multipliers, things like a half or pi. It also completely ignores trigonometric, logarithmic, and exponential functions. So while dimensions can absolutely prove an equation is physically impossible, they can't verify if your math coefficient is actually correct.
And finally, Section 5, deducing formulas and limitations.
This is a classic exam archetype. Imagine you're given a scenario where the time period of a pendulum depends on the length of the string, gravity, and the mass of the bob. The question is, if we know these ingredients of the system, can we use dimensions to reverse engineer the exact mathematical recipe? Turns out, yes, we can. We just follow this simple four-step workflow. First, we write out the variables with unknown exponents. Let's call them x, y, and z. Second, we substitute the dimensional formulas for both sides of the equation. Third, we just match up the exponents for mass, length, and time on the left and right sides to create some really basic algebraic equations. And it's practically magic. When we solve them, we find that the exponent for mass, z, is exactly 0. This proves mathematically that the pendulum's mass doesn't matter at all to its time period. We plug the other exponents back in, and boom, we get our formula. Time period equals a constant k times the square root of length over gravity. That is an incredibly powerful tool to have in your back pocket. But reality check. You absolutely have to remember these critical limitations for those tricky conceptual exam questions. This deductive method completely breaks down if the true formula involves a sum or difference of multiple terms. It also fails if your system depends on more than 3 independent base physical quantities, mainly because we only have m, l, and t to balance with. And, like we touched on earlier, it totally fails if trigonometric, exponential, or log functions are tangled up in the changing variables. We've covered some serious ground today. We've built an incredible toolkit, starting from those unchanging base units, mastering the precise counting of significant figures, and working all the way up to formula deduction using the homogeneity lie detector. So as you stare down your prep materials today, the only question left is, how are you going to take these cheat codes and completely deconstruct your next impossible exam question?